write in Python just an example of the parser cleaning procedure that we have seen yesterday. Okay. So the idea is that we are going to generate some points and then run the k-means algorithm on them. Of course, we want to generate the points so that they are somehow clustered. And okay, for that we're going to use the NumPy library, which is already included in in this lab's computers. So let's try to work on it. So let's just edit a Python file. I'm going to call it kmeans.py. So the idea is that we have to proceed step by step. The first step will be, let us generate a cloud of random points. But the cloud of random points that I want is not evenly distributed. I want to distribute it as a multivariate normal, so a Gaussian, with a Gaussian distribution on n dimensions. For us, n is the number of dimensions. Of course, in order to see something, we will use n equal to 2. But then again, I would like to write the code so that it's as general as possible. So, let us say that we want n dimensions, that we want to generate 100 elements with a multivariate distribution in 2 dimensions. And we want to do this by using the NumPy package. NumPy has a class called random that includes many random generation functions, and in particular we have the multivariate normal method. The multivariate normal method requires 3 arguments. The first is the mean of the of our distribution. The second is a covariance matrix that tells how much our distribution is spread out. So the idea is that we need to create a suitable mean position, and to do this we can create an array mean. We can use so of course our next objective will be to create many clusters with different mean positions. So we will also generate the mean position in a random way, but in this case the mean position of our cloud will be uniformly generated, let's say between 0 and 1 in n dimensions.
Sorry, you mean mean position by centroid or middle?
Sorry?
You mean mean position by centroid or middle of the cluster?
Centroid. But actually, in this moment I'm not talking about clusters. Okay, I just want to generate point having a multivariate normal distribution. Of course, the mean position will be approximately the centroid of that cloud of points. We are not requiring our central point to be one of the points, so I'm not talking of medoid but of centroid. Okay. So in this case, okay, I just want to generate a vector, which I call mean, containing n random number. These random numbers will be generated uniformly between 0 and 1. In fact, let's forget for now the other instruction. If I print the mean, I should get okay, just a vector of two random numbers in 0, 1. So let us use this vector as mean value, so I remove this print. But the second object that we need in order to generate a multivariate normal is the covariance matrix. The covariance matrix, let's call it covariance. So in NumPy we have a function, probably it's identity, that generates an identity matrix. Again, we need it with dimension n. But let me check that this generates a good covariance matrix. Okay. Actually, I want my distribution of point to be isotropic. I don't have particular directions on which it should elongate or so. So I just want the identity matrix. Actually, I want the distribution to be rather concentrated around this point. So, well, but we shall see it later. Once we have the mean and the covariance, we can finally use the multivariate normal function to generate a set of samples drawn by the multivariate normal distribution having this mean and this covariance. Let's say that I want to generate m points. Okay, I already set m equal to 100. This will generate a set of m points having this distribution. And of course, we need to assign them to some vector. Let's call it d. D is the set of our samples, as the nomenclature of yesterday, and we can see what happens by printing d. If we print d, we get a distribution, a set of points having that distribution. Well, actually, I would like to see this distribution on screen. Okay, I would like to plot it. For that, I suggest we use GNU-plot. I don't know if you are familiar with it. So, let's say, let me show you on the terminal. GNU-plot, okay, it's just a simple program that responds to commands to plot something. For example, if I write plot the sign of x, it will output a window showing the sign of x. Again, I can ask it to plot the functions or to plot the points taken from a data file. So the only thing I need to do to show something is create a data file and then run gnuplot on that data file. So let us go out from gnuplot. I want to use gnuplot from inside NumPy. So let's do this. Well, I can do it here. Rather than printing D, I want to output D as a I want to output it to a file. So let me open a file. Let's call it well, D. I want to write it, so W. And then simply for every element small d in big D, I will write this point on in the file. How do I want to write it? As a tuple of numbers separated by spaces. So what I want actually to write is the elements of D joined by spaces and terminated by a new line. Finally, I close the file. Before going further, let's see if I create the file correctly. Okay, I forgot one thing. So the join function requires strings to be concatenated. So actually I need to convert the elements of D, which are numbers, into strings. So I just map the function str on the elements of D. Okay. Given, so uppercase D is a vector of points, so a vector of vectors of numbers. For each of these vectors, I take the corresponding list of strings, I concatenate them with spaces in the middle, and I add a new line. So now it should work. Okay, if I look at the file D, okay, you see, now we have the list of points. Now, let me show you gnuplot from its interactive shell. I can tell gnuplot to plot the file D, uppercase D. Okay. So the function plot requires either some function or a file name which is written between double quotes. And if I ask it to plot D, I get actually a plot of my point distribution. Of course, the distribution looks, it doesn't look perfectly isotropic just because, okay, the window is rectangular and the distribution of point is not perfectly even. But that's not a problem. I just wanted to see the points. Now, in order to exit from gnuplot, either Q or Control D. Actually, I would like GNU-plot to be run directly from the Python script. So let me just write the command file. So let me reopen f as a file containing the commands for GNU-plot. Let's call it cmd, for example. And in f, we can write the command plot open quotes d closed quotes. But let's see if that's enough. I close f. Then I want to execute an external command, so I import the OS library and I call the system method. And what I want to execute, to ask the shell to execute, is GNU-plot cmd. There are many ways to do that, so you may have your preferred commands. There is also an internal Python library that interacts with GNU-plot. So I don't remember its name, but it exports all functions that automatically interface with GNU-plot, or if you prefer, with R or with other plotting facilities. Anyway, I think this is a little easier, at least for me. So let's see what happens if I call Python on this. Okay, it probably worked, but I could not see anything. Why? Probably because after plotting the file, I need to let's see. Well, no. Let's do this. Let me write a more complex string. So I don't know if you're familiar with the triple quote notation in Python. It means that I can write everything in here without having to care about escape characters or quotes and so on. I can write everything verbatim and it works. So I want to create a PNG file. So the output terminal in our case will be a PNG file, and the output will be called, I don't know, t.png. Okay, so these are the three commands that I want to pass to GNU-plot. I put them into file cmd, and then I invoke GNU-plot cmd. Let me just check if it works. Now, if we look here, we should have, okay, file d.png, which we can proceed to open with, okay, open d.png, no. What is the one program in Linux that displays pictures.
Maybe GView. I don't know what that is. Or GThumb.
No. G?
Thumb.
No. Okay, I just open this and have a look at d.png. Okay. So this PNG image has been generated by the Python script via.
It's EOG.
Sorry?
EOG. EOG. The program.
Okay. So EOG.
Yeah.
Oh, great. Thank you. Okay, so here we have a way of generating points and a way to plot them. Now, we actually want to generate more than one cloud of points with different means. To do this, let me slightly modify the code. Rather than generating one single mean point, I create as many mean points as I want. Well, let's decide how many. So let's say that I want to generate 3 clouds of points. Okay, let NC be the number of clouds of points that I want to generate. And let's say that I actually want 100 points in every cloud. So NE is the number of elements in each cloud. So that actually our overall number of points M is just NC times NE. Okay, so now I'm generating 300 points in groups of 100, each having a different mean. I can generate all means in a single shot by saying that I want NC rows of n columns each. So now I'm generating NC vectors, each of which is uniformly distributed from 0 to 1. Okay, this is my way to explain that I want actually a 2-dimensional array with NC rows and columns. In fact, we can print it and then maybe let me also import the sys package so that I can print and then halt the program. I just want to print out the means vector. Okay, so I generate a vector of mean points. I only want one covariance matrix. I want it to be valid for all points, so I'm keeping it as it is. And now I need to generate NC different distributions, NC different multivariate distributions that differ from each other because of the mean value. So just let's just make a for loop for every row of the means vector. Well, actually now I need to maintain D as the concatenation of 3 different distributions, in general of NC different distributions. So let's start by setting D as none here. Here I let us generate this multivariate normal distribution, and we call it okay, dist. Then I need to concatenate dist to the existing D. So D contains all distributions together. Of course, if D is none, then I just put dist into D. Else D will be the vertical stack of, and here I need a pair, which is the previous D and the current value of this. Okay, in this way I am going to, and of course I want NE elements for each distribution. So let's see it again. So I want to generate NE elements having this mean, and I concatenate them to all the others that have been generated by this loop. At the end, I will have NE times NC, so a total of M elements drawn from 3 different distributions. Let's see what it means in terms of output points. So we can just rerun this and then have a look at d.png. Well, you see, what happens is that actually we generated 3 distributions, but we cannot see it just because the covariance is too large. So actually I've been generating 3 distributions that overlap a lot. So let me reduce them for example by taking the covariance matrix and multiplying it by a small scalar, 0.05 for example. Okay, if I do it, well, apparently that's not enough. Let's put another 0. Okay, now we start to see separate clouds of points. Actually, of course, we are generating them with a random number generator, so every time we run the program we have different distributions. Okay, because every time NumPy will start with a different random seed. So what I suggest now is that here at the beginning, we set a random number seed and apply it to the random number generator of NumPy. So that every time we run Python, we get the same distribution of points. Okay, now remember, okay, you see how it is now with the seed equal to 1. You should get exactly the same result. Next time I run Python, now I get exactly the same cloud. So it should be easier for us to work if we have always the same result. Okay, now we have generated our cloud of points. We have a way to display it. Now, let's say now I'm going to take the instructions to generate the plot and enclose them into a function so that it will be easier for us to use it later. So let's say I call the function just plot. The only argument of this function is the set of points that we want to plot. Of course, we need to take everything else and indent it so that plot understands that these instructions are inside the function. Well, let's say that we want to choose the name of the image file. So rather than call it t.png, we put whatever name is passed to the function like this. Okay, now we can take this function and put it on top somewhere, for example here. So that here at the end we just need to call plot, for example, t.png and t in order to have our points. As always, let me check if everything works. Apparently it does. Well, to be sure, let me remove t.png and run Python. Okay, it generates the picture. Okay, is everything okay now? So we just prepared the setup for our test. Now we have a cloud of points that we want to clusterize. Now, okay, I remove this plotting function for the moment. Okay, from now on, we want to run our hard k-means algorithm on this cloud of points. Okay, to do it, we first need to, Okay, first thing we need to decide how many clusters we want. So let's put k equal to 3. Now, as you remember, we want to start with a set of let me remind you. So, Ci for I going from 1 to m is represent the cluster to which document I belongs. Okay. And in the hard k-means procedure, we usually start by assigning random indices to Ci. So Ci for every I will be a random number from 1 to k. Or let's stick to the Python definition of arrays and so on. So all our indices will start from 0. So actually, Ci will be a number from 0 to k minus 1. So we just create a vector C using I don't remember which function, but you can find it easily. Let's go to NumPy. Random sampling. I want to get okay, random integers. The function is random integers. And the arguments will be from to, okay? This means that every integer will be a number from 0 to k minus 1, okay? K is excluded from the range. And also that I want m elements. So that if I actually print C, what I get is okay, a set of 300 integers. Oh, well, should be from 0 to 2. Okay, so actually k is included. I didn't expect it. Oh, it's the largest, right. So here I have to put k minus 1. Okay, so let me correct what I said before. K, the second argument is the largest number that can be generated. So now we should hopefully get numbers from 0 to 2. Okay. So these numbers are the initial distribution of documents of the elements D into clusters. Now we need to compute the centroid of each cluster. Okay? So, to do this, well, we should generate, I want mu to be a vector of vectors. Okay? Containing a number k elements of n numbers each, which will represent my k centroids in the n-dimensional space. So how do I generate it? I want mu to be the sum of different see, I want mu to be an average. So I want to initialize it with zeros. So first thing I do is, let's see, how can I generate rapidly an array of zeros okay. We have here a function, zeros. Okay, numpy, zeros, and then the shape of the array. Zeros without an E. The shape of the array means a list of the number of items in each dimension. I want a two-dimensional array with k rows and n columns. Sorry to go slow, but I want to check every step. So let's see if k is what we want. Okay, so mu now is a set of 0 points. Well, now let's just iterate through all elements in D. Well, actually, in order to compute the average, I also need to count the elements in each cluster. So let's say we have another list n. In this case, no, I'm not going to use the numpy initializer. Let's just say that it will be simply this, okay? A list with k zeros. Now, for every element in D, we increase the number of elements corresponding to the cluster to which I belongs. And we add to the corresponding mu the ith element of D. I'm not sure if this works. Now we shall see. Next, for all cluster indices we take mu of j and we divide it by n of j. This should give us the centroids of the clusters, and let me see if it works. Okay, I forgot the column here. Okay, so you see now so after these two loops we have the centroids of each cluster. Now I would like to print them, to draw them. And possibly I would like to draw not only the points and the centroids, but also to have different point colors for each cluster. So let's just we go back to the plot function and let me make it a little more complex. Now, I don't only want the set of elements D, but I also want a set of cluster attributions C and the centroids O. Now, the trick for having different kinds of points, the simpler way to do it is just to save the points of each cluster. Well, actually there are many ways to do it. For example, we can just save all elements on one file and tag it with different names. So with some, well, let's do the simplest way. We just save the points of each cluster on a different file. Which is rather easy to do because instead of opening just one file, I can open a list of files, each having a different name. Like this. Let's see, the number of clusters is the length of vector loop. Okay, like this, I'm opening files D1, D2, D3, and so on until k-1. Next, I only have, for every document, for every item in D, well, actually, I want to work on indices now. So for I, spanning the set of indices of my set of elements, I just need to, as before, I'm not going to call it lowercase d, but the ith element of d, okay, I modified this. No, sorry. And I want to write it on what file. Remember that now F is a list of files. And the file I want to write it in is simply C of I. And now, of course, I want to close all files, so let's just close all files in this list. Okay, so I take every element in my set and I just decide on which file I want to write it. Next, I also want to write a file containing the centroids, so the mu. Let's call it mu. And for all m in my vector mu, okay, and it will be something very similar to this. Of course, here I have m. Okay, so first I distribute my points in different files. Then I create a file containing the centroids, and now we have to plot all of these elements. So what we can do is, okay, we start by plotting mu. Then here the trick is this one. If I want to plot many files, in this case I want to plot, the command to plot many files will be plot mu, comma, d0, comma, d1, and so on. Okay, I want to generate this, this command. So I start by plotting mu, like this, and then, okay, space here. On the same line, before closing the file, I just run like this. I write comma, double quotes, d followed by a number, close double quotes, where the number is j. Okay, so if the length of mu, which is the number of clusters, is 3, I will write comma d0, comma d1, comma d2. At least this is what I hope will happen. Let's see if it really happens. So let me go back here. I remove all files that have nothing to do with us. So I only want to keep k-means.py. Okay, there are also other directors. If I run Python k-means.py, it actually didn't work because I forgot to invoke the function. So remember, the function is plot and it requires name, set of points, set of cluster attributions, and set of centroids. I forgot to call it. Plot Again, the name, okay, for the moment it will be just d.png. Set of elements is C, set of cluster attribution is C, and set of centroids is B. Now we should get some more files, okay. So here we have the set of points belonging to cluster 0, the set of points belonging to cluster 1, the set of points belonging to cluster 2, the set of centroids, okay, much smaller, only 3, the command file, okay, I forgot to put a new line at the end, but it's the same, and our set of points and centroids. Okay, the picture is a little confused because you see the key is here. Let me move it there so that we can see everything. We just need to add a comment here. It should be set key top left. Okay. So this is the first step. So elements have been attributed randomly to the 3 different clusters. The centroids are the red crosses. Of course, as expected, they are more or less in the middle because points of every cluster are in every cloud. But actually, this is what we expected, okay. Now, let's iterate a couple of times so that we see what happens. So, let me close it here. And let's go back to the k-means program. Okay, so here we have computed the new centroids. And as you remember, after computing the new centroids, we need to recompute the cluster attribution of every document. We can do this simply by iterating all items, finding the cluster centroid which is closer to it, and assuming that that is the cluster to which the document belongs. So here, after plotting, so from here to here, we are computing the new centroids. Now, for all M elements, well, actually we can combine everything into one single instruction. Simply, the new cluster of I is the closer centroid, the closest centroid, okay, we can later define this function that just given our item, which is, sorry, it is t of y. So the item and the set of centroids provides the index of the closest one. And we assign them to C of I. Next, okay, we just need to iterate this for a number of steps. So let's say 5 times. Okay, is that okay? So just recompute CI. Of course, here we need to define this function, closest centroid. So let us define it. So closest centroid is a function that requires an element D and a set of centroids too. Okay, so just we need to remember, so we need to minimize the distance. So we just do it the classical way by defining a minimum distance as a very large initial number. The index of the minimum distance, okay, we don't actually need to initialize. Let me initialize it to a strange value. And then for every cluster J, for every centroid J, for the length, for the number of existing centroids, well, let the ds be the distance between d and mu of j. Of course, later we will have to define the distance function. Let me see if NumPy already has this function. Well, it could be binary in the sense of bits or not. I don't think they are even mathematical functions. Okay, but I think we have everything. Well, let's call it distance then. If the current distance is less than the minimum distance, then of course minimum distance becomes the current distance and the minimum index becomes the current index. And then at the end we just return the minimum index found, which is what we want. Let me define the distance between two generic vectors x and y. Let's see if we can do it nicely. So we need to take the difference between the vector, that is the difference between x and y. We need to compute the square of every input, and we have this square function to do it. And next we have to add all elements up. This is an element-wise addition. Okay, just I sum the squares of the differences. That should do it. Of course, I want to return the result. This is not the distance, this is the squared distance. But there's no reason to compute the square root. We only need the distance to compare. We only need to compare them, so should be okay. Now, of course, I want to generate a different picture for every step. So instead of calling d.png, I will call it d0, d1, d2, d3, and d4 for the 4 steps. Again, I need to see if this works. Okay, we generated 4 PNG functions. Now, let's see if I can open all of them together. Okay, so this is the first step, d0. Okay, d0 has the 3 centroids, well, actually in a rather unpleasant position, but in the second step, one of the centroids has been captured by this pair of clusters, the other centroid has been captured by the other cluster, and this has a marginal position. Let's see if things improve from here. Of course, they are going to improve because at the next step, this optical mice and very black tables are not very compatible. Okay, now this centroid is going to capture all the elements above approximately this line. So in the next step, this centroid is going to conquer its own cluster. Sorry, I went back to the first picture. So after 5 steps, actually the 3 centroids have moved to the center of their clusters. Actually, we were very lucky, because if this centroid had been slightly moved away, it would probably never capture these points, and maybe it would have disappeared because it did not have any point with it associated to it. We shall see later how we can deal with this if we have time. Okay, so now we have seen what happens with the 3 centroids. Let's see what happens with a different number of centroids. Well, rather than setting the number k here, we can just make k vary from 1 to, comma, 1 to 5. Okay, 6 is excluded, I think. Okay, everything should be the same. The only point here is that, okay, let me also put the cluster number, the value of k in the file name, so that, okay, we are going to generate a different set of pictures, each having a prefix k1 for one centroid, k2 for 2 centroids, and so on. Let's see how this works. Okay, well, oh, okay. The problem is that one of the clusters did not get points, so the Python output not a number because it was a 0 by 0 division, and NuPlot was not very happy with it. Actually, let's say maybe it still worked. So this time I want all the pictures that start with K. Okay, this is the case of one cluster. Of course, it's very boring, and from step to step, we still have the same picture because we're never going to change the cluster attribution. Let's go to k equal 2. Okay, in this case, as you see, the two clusters as centroids are slightly separated, so this will be clearly pulled up here, while this will be pulled down here. In the next step, you see that this centroid has almost captured all of this domain below, apart from some points which were marginally closer to the other one. But it's not a problem because at the next step, everything below this line has been conquered by this cluster, and the clustering is complete. Of course, here we could set a termination criterion, as I said last time. If nothing changes, then stop. In this case, I just run it 5 times, even if there is no need for that. Let's move to 3. Okay, the case of 3, like before, requires a little time, but finally, we get to it. Actually, I cannot see the third centroid. You see, I cannot see the centroid of the blue cluster, but maybe it's only covered by some element here. Anyway, you see, after 4 steps, the clustering is not yet complete because probably there are some points that are going to move from cluster to cluster. But as you see now, we are already in a good shape. With 4 elements, okay, this was the error as before. Later we will code for this error. Okay, both for 4 and 5 clusters. Okay, let's correct the problem. What I propose is that if the number of elements in a cluster is 0, we simply don't plot that centroid. So we can see what happens. Of course, the real action to take in this case would be, okay, that centroid is useless, let's put it somewhere else. But just to be faster, let's say, okay, here, okay, I just divide if n of j is strictly larger than 0. Otherwise, I don't do a 0 by 0 division. So, every centroid corresponding to a cluster without points will remain 0. Next, I also pass the n vector, the vector containing the number of points in each cluster, to the plot function. And here I modify it so that okay, here I don't write centroids that correspond to empty clusters. To do it, let's say, instead of iterating directly on the elements of move, I iterate on the indices. So it becomes like this. So I write the move of j, but only if the corresponding number of elements in cluster j is strictly larger than 0. And also here, I plot the file dj only if the number of elements in that file is different from 0. Otherwise, I would have an empty file to plot. Like this. Okay, so now if I have empty clusters, they shouldn't appear in the drawing, the plot. Okay, there was an error. Right. I forgot to put the argument here. Okay, here we go with 1 cluster, with 2 clusters, with 3 clusters, with 4 clusters. Actually, one of the clusters, okay, it came back from 0. So you see, with 4 clusters, we still have, but the fact that one of the centroids moved again in is just accidental because it was placed in 0 when it wasn't used. Okay, so it's actually an artifact. And with 5 clusters, we have even more complex separation like this. Okay, so in this case we had one clearly separated cluster that has been found every time, and the more complex situation here. Now, I would like to see what happens to the quantization error for different values of k. Okay, let's run each of the iteration procedures a couple more iterations so that they get more stable. Or, if you prefer, let's do it like this. I repeat this loop, the clustering loop, indefinitely. The step counter will be 0 here, and it will be incremented here. But I want to stop when no more changes happen to the C vector. So that I add a flag here, initially equal to false. I set I find the closest centroid, but before assigning it to Ci, I check if Ci is different from new C, then it means that something has changed from the previous iteration. And in this case, of course, I want to set the new value into Ci. And after doing this, if nothing has changed, sorry, this is not C, it's not changed, then we can just write. I don't like it like this. Let me put just change here. Let's say one changed. So we don't need this, okay? So, while there is a change in the cluster attribution from one iteration to the next, we keep recomputing. If no changes happen, then we stop and we move to the next value of k until k is equal to 5. So actually here now we should have a measure of how long it takes And in fact, some of the procedures required a lot of steps. In particular, K5 converged after 21 steps. K4 converged after 11 steps. By the way, in this way now I'm not having them in the right order. So I need to represent the step with two digits. So that now we have, oh, I forgot to remove the ones that were generated before. Let me remove all the PNG files and rerun Python. Okay, now they are in the correct order. So we can have a look at what happened. So the first, for k equal to 1, we are already in the correct clustering, so only one step has been required. For k equal to 2, we have 2 steps before everything is set up. Then we are done. For k equal to 3, we have a few more steps. Okay, so after the 5th step, everything is settled down. For k equal to 4, you see there are marginal movements of the 2 lower centroids before we are settled down. For k equal to 5, again, we have lots of small movements of the lower centroids before everything works. Okay, finally, let us print out the quantization error so that we see actually what happens when k, the number of clusters, increases. Well, to do it, we can ask the closest centroid function to return not only the index of the centroid, but also the distance from that centroid, which is stored in MD. Okay, so closest centroid returns the index and the distance of an item from the closest element of group. So I return a pair. This pair can be assigned to the 2 variables new c and new d. And here we initialize the quantization error to 0 at the beginning, and then we simply add the new distance to E. Remember that the distance is already squared, so we don't need to square it again. So finally, before proceeding, let's just write it out. Well, no, I want to write it out only at the end. So I want to write the last quantization error for every step. I don't mind about the other. So I write it here. Just write it on the screen. let's say I want to know for a given value of k the number of steps that it has taken to converge and the final quantization error. And I get them as, okay, the value of k is k, the number of steps is the variable step, and the quantization error is the last value of it. So let's save it and run. I forgot to put a new line. Okay. So what actually happens here? Okay, the first column is the value of k, so 1, 2, 3, 4, 5. Is that, okay, this is the number of steps required to converge. It's normal, of course, it's going to become larger when many centroids are involved. Here, you see that we have, in fact, very significant reductions of the quantization error in the first steps, from 32 to 6 to something between 2 and 3. But in the following steps, it starts reducing much more slowly. So actually, k equal to 3 is a good indication of the actual number of clusters, because it is the last large reduction of the quantization error. What happens after k equal to 3 is a much more marginal reduction. So actually, this should tell us that 3 is the right number of clusters. Of course, this depends a lot on how things are set up. For example, let's change the seed. Okay, so we just generate another set of points. Okay, again, 3 looks like a good number to stop. If we look at what happened here, well, in this case, probably all mean values were rather central, so we don't have 3 clear clusters. But again, if we look at what happens with 2 clusters, which requires, okay, it stopped here, or with 3 clusters, no, this is the last. Okay, you say what's happening here with 3 clusters. Actually, the third cluster here was rather marginal at the beginning, but then it conquered a slice in the middle, and then we have this interesting rotation, which we end up with this clusterization, which is probably the right one. We should check, of course, by looking at what was the intended set of clouds. Okay, again, with 4 elements we have local movements until we settle down to this configuration, which does not provide a very significant decrease in the quantization error, and then 5 clusters. Actually, you see, with 5 clusters, we actually have only 4. The 5th point was out of, did not get any point, so it was left out. The problem is what happens when, let's see, okay, rather than putting a constant here, let's call it, okay, how the cloud is spread. So this was the number that I was using as the covariance. Let's reduce it. If I reduce it, what I get is, okay, actually it still worked. Let's see what happens. Okay, now the 3 clouds are much more localized. So the program finds everything more easily. But if we reduce it too much, something bad can happen. Like in this case. In this case, as you can see here, the 3 clusters are very localized. So, let's look at what happens with 3 clusters. With 3 clusters, something rather bad happens. Because at the beginning, the 3 centroids are more or less in the center, but at least for this particular choice of random seed, this cluster, let's see, yes, probably this cluster is not close to, is not the closest to any point. All points here are closer to this one. All points here are probably shared between these 2. All points here are closer to this one. So this cluster center in the next step is going lost. And if we don't set the lost cluster center position in some good place here, we are actually continuing with 2 clusters. So what can happen is that even in a good situation like this, we actually have to pay attention to some bad effects. Even if this is a naturally 3 cluster system, and it's very well separated, one of the 3 centroids has gotten lost because it was not close to anything at the beginning. What procedure could we suggest in this case in order to put the lost centroid into place again? For example, one possible action is this. Look at the 2 centroids. How do they contribute to the overall quantization error? You see, this centroid contributes not so much, because all points associated to this centroid are rather close to it. This centroid contributes a lot more to the quantization error because all distances between this centroid and its corresponding elements, okay, all distances are large. So one possible strategy is this. If we lose a centroid because it's not associated to any cluster, then let's move it to the proximity of the centroid that contributes the largest value to the quantization error. In this way, the lost centroid would be placed here, and probably the clustering procedure could proceed by splitting the two centroids along the two remaining clusters above. So we have no time to test this procedure now. But again, we need to take care also of cases where everything seems to go well, but actually because of numerical, because of issues that naturally occur when you place points randomly here and there, okay, we need to take care of that. Okay, so in the next days, anyway, I will put this code, well, I will comment the code a little and then put it on the website. So if you want to experiment with it, of course, you can do it. Okay, I think it's all for today.